So we're going to do integration by parts. Integration by parts is another technique for integration. Just like the substitution is a technique for integration, it undoes the chain rule. Integration parts is a technique for integration. It actually undoes the product rule. So let's start with the product rule. I want to show you what this method looks like. So let's start with the product rule. So the product rule is that the derivative of a product so the derivative of f of x times g of x is the first times the derivative of the second plus the second times the derivative of the first. So it's f of x times g prime plus g of x times f prime. We want to actually know what the integral of that product is. So we're going to take the integral of both sides. So we have the integral of the derivative of f of x times g of x is equal to the integral of f of x times g prime of x, forgot my dx, plus g of x times f prime of x, d of x. The fundamental theorem of calculus tells us that the integral of a derivative is just a thing inside. So the integral of the derivative of f of x times g of x is just f of x times g of x. We also have a property that says we can actually separate these two integrals out. So this will be the integral of f of x times g prime of x dx plus the integral of g of x times f prime of x dx. All right. So we happen to have this. We want to find out what this is. And what we actually want to do is we actually want to know is what is the integral. And it doesn't matter which one you do. We're going to go ahead and pick out, we want to know what the integral of f of x times g prime of x is equal to. So that is equal to, if I were to just do some algebra on this, the integral of f of x times g prime of x dx is equal to the f of x times g of x minus the integral of g of x times f prime of x dx. This is actually known as the integration by parts. What you have to do integration by parts is you have to figure out what do you want to call your f of x, what do you want to call your g prime of x, and then knowing those, you can find f of x, g of x, you can find g of x and f prime of x. So we need to figure out what these are and guess them. Some people like to use u's instead of f's and v's. So sometimes you'll see people write this as u times dv, u being your f of x, dv being the g prime dx, is equal to u times v minus the integral of v. G of x is going to be the v because g prime is dv. So v times du, because f prime dx is the du. So you'll see me probably write it this way. I like to use it this way instead of f's and g's. I think it gets too confusing. So let's go ahead and try to find some examples of this. Let's actually look and see how this works. So we have the integral of x to the fourth natural log of x dx. I would like to find out what that integral is. One thing I do want to point out to you is that you want to try substitution first. This actually, integration by parts, is the last technique you mostly want to try. Usually you try integration by substitution first. If that doesn't work, you're going to try some other techniques which you'll learn in other places, you'll learn later. But this is probably the last one we actually try to use. So even though we're teaching it to you now, it is actually one of the last ones you try. It's kind of your go-to if nothing else works. So what I've got is I've got the integral of x to the fourth natural log of x dx. And I would like to find out what that integral is. And I'm going to use this idea of integration by parts because I notice I do have a product. So that's one clue that kind of tells me to try that. Though I've had products before, I try substitution, it probably won't work. In fact, if you want to try substitution, let u equal the natural log of x. The derivative of that is 1 over x. I don't have a 1 over x anywhere. So that won't work. But what I can do is I can think about letting u be something and dv be something. dv has to be something you can find the integral of. Because if you look at this formula, we have a dv, and we're going to take the integral of it to find out what v is. So you have to actually pick something that you can find the integral of. And I can't find the integral of the natural log of x. I don't have a formula for that. It's not one of my basic formulas. But I can find the integral of x to the fourth. I also happen to know the derivative of natural log. So I'm going to actually let u equal the natural log of x. I'm going to let dv equal x to the fourth dx. I'm going to let u equal the natural log of x because I can find the derivative of natural log of x. Let dv equal x to the fourth dx, everything left over when I pulled that out. And I can do that because x to the fourth, I can find the integral of that. So now what you're going to do is you're going to find out what the derivative of u is, what du is. That's going to be 1 over x dx because the derivative of natural log is 1 over x. And then with the dv, you're basically thinking of taking the integral of both sides. So the integral of dv is v. The integral of x to the fourth is 1/5 x to the fifth. You don't worry about the plus c here because it turns out that you're going to get a plus c in the end, and the plus c just makes things more confusing right now. So don't worry about the plus c at this moment when we find this integral. So now we can go ahead and do the integration by parts. Integration by parts is u times v minus the integral of v du. So you're just going to be substituting in. U is the natural log of x. V is 1/5 x to the fifth. V is 1/5 x to the fifth. Du is 1 over x dx. So what we now have is 1/5 x to the fifth natural log of x minus 1/5 the integral, well, x to the fifth times 1 over x is x to the fourth dx. Notice you still have an integral to do, but I know how to find this integral. So even though I end up still having an integral, it's one I can do. So what this method does is it allows me to take something that I don't know what to do with and make it into an integral I can find. In fact, x to the fourth is 1/5 x to the fifth. I have that 1/5 already out front. And now I do the plus c because I'm now done taking integrals. So I end up with 1/5 x to the fifth, natural log of x, minus 1 over 25 x to the fifth plus c. Let's try a few more of these. Let's try the integral of t cubed e to the t dt. In this case, again, you want to ask yourself, if you're going to do integration by parts, you have to ask yourself, can you find the integral of both of these? And I can find the integral of both of these pieces. So that kind of tells me, oh, I can do that. I don't need to actually go through and pick that. That wouldn't be my criteria for picking. The next criteria for picking, if you can find the integral of both pieces, is you want to make things simpler. If I let dv be t cubed, when I took the integral of that, I get t to the fourth. That's not simpler, that's more involved. So if I want it to become simpler, I usually want my u to be t cubed and my dv to be e to the t dt, because I now take du would be 3t squared, which makes it simpler, dt. So it became a lower power. And what I mean by simpler is it got a lower power. Then I'm going to take the integral of the dv, which is v. The integral of e to the t is e to the t. So again, my rule is u times v minus the integral of v du. I usually write down every single time so I can remember what I'm doing. U was t cubed, v was e to the t, integral of e to the t, and then times du. Du is 3t squared dt. So we now have t cubed e to the t minus 3, the integral of t squared e to the t dt. Well, looking at that, yeah, I'm not done because I still know how to find the integral of t squared e to the t. So what we do in this case, if we do integration by parts again. So we now pick a new u. for this new one, u is now going to be t squared. Even though it didn't get to something I can do, it got simpler. T squared e to the t is way simpler than t cubed. So we're going to do t squared for u, and the dv will be e to the t dt. Du, therefore, is 2t dt. dv, the integral of that is v. The integral of e to the t is e to the t. So we now have, we still have that t cubed e to the t there. That's not what we're dealing with. That was just an answer. We didn't need to do that. That was a function without an integral. We now have the minus 3. Now we need to do that integral, the integral of t squared e to the t. And again, that's going to be u times v minus the integral of v du. So u was t squared, v is e to the t, minus the integral of v, which is e to the t, du is 2t dt. So we have this t cubed e to the t here, minus 3. I'm going to go ahead and multiply the 3 times. That'll be minus 3t squared e to the t. Minus 3 times minus 2 is plus 6. The integral of e to the t dt. Again, I still don't know this integral, but it's getting simpler. Notice I went from t squared now to t. So let's try integration by parts again. So here u would be, pick one again, make it simpler. So let u be the t, dv equals e to the t dt. Du is therefore equal to dt, and the integral of v, dv is v, and the integral of e to the t dt is e to the t. So again, we have this t cubed e to the t first, minus 3t squared e to the t next, plus 6. Now we're going to do this integral. Again, the rule is integration by parts is u times v minus the integral of v du. So we have u, which is t, times v, which is e to the t, minus the integral of v, which is e to the t, du happens to be dt. So looking at this, I have t cubed e to the t minus 3t squared e to the t plus 6t e to the t minus 6 times the integral of t e to the t, but the integral of e to the t is e to the t. So I have minus 6 e to the t. And then since I'm now done taking all my integrals, I have my plus c. You could have had your plus c all along the way. That gets kind of really ugly and gets nasty looking, but you could do it. It just really gets really hard to work with. All right. So sometimes you have to do integration by parts several times. Let's try another one. This is the integral of e to the minus theta cosine of 2 theta d theta. Again, I notice I have a product going on here. I've got some nasty things going on here. I don't see anything that would be substitution. So we're going to let u equal. Again, pick one that you want your dv to be whatever can't be, what you can't find the derivative of. In this case, or what you can't find the integral of. In this case, I can find the integral of both. It really is up to you which one you want to use. I'm going to go ahead and let u equal cosine of 2 theta, and dv equal e to the minus theta d theta. So my du would be minus 2 sine of 2 theta, because remember you take the derivative of the outside, which is the derivative of cosine is minus sine, and then times the derivative of the inside. The derivative of 2 theta is 2. The integral of v, the integral of dv is v. The integral of e to the theta, well, you have to do a little bit of substitution here. So sometimes we have to do substitution in this because I have an e to the minus theta, not e to the theta. But if I took the derivative of that, I get minus. So I'm just going to get e minus e to the minus theta. Okay. So now this gives me the integral. I'm sorry, not the integral. This gives me, again, using u times v minus the integral of v du. U was cosine of 2 theta. v is minus e to the minus theta. So we have minus e to the minus theta cosine of 2 theta minus v, which is minus e to the minus theta. So it looks like it's going to be a plus. But du is minus 2 sine of 2 theta. So that will make it minus again. I'll put the 2 on the outside. D theta. I forgot my d theta. Okay. So again, I have to do this again. I'm going to do use of integration by parts again. I'm going to do the same thing. I'm going to let u be the sine of 2 theta in this case. Because I want my dv to be the same thing. So don't go changing them. Usually it doesn't help you to change them. So u is equal to sine of 2 theta. So du is equal to 2 cosine of 2 theta d theta. dv is equal to e to the minus theta d theta. So v will again be minus e to the minus theta. So let's see what we have now. We have the integral of e to the minus theta cosine of 2 theta d theta is equal to minus e to the minus theta cosine of 2 theta minus 2 times, again, doing integration by parts. U times v minus the integral of v du. U is sine of 2 theta. V is minus e to the minus e to the minus theta. So I have minus e to the minus theta sine 2 theta minus the integral of, it looks like I'm going to again have some couple minuses going on here. So I have minus and that minus, so it becomes plus e to the minus theta. And then I have this 2, and I've got the cosine of 2 theta d theta. Well, so let's see kind of what we have now. We have the integral of e to the minus theta cosine of 2 theta d theta is equal to minus e to the minus theta cosine of 2 theta plus 2 e to the minus theta sine of 2 theta minus 4 the integral of e to the minus theta cosine of 2 theta d theta. Well, we're not done. We still have this integral. We can't get rid of the integral. And so you think, well, maybe I'll just try it again. But I noticed that I have integral of e to the minus theta cosine 2 theta d theta on the right-hand side of the equation. I also have it on the left-hand side of the equation. So I could do some algebra here. I could add 4 integral of e to the minus theta cosine of 2 theta d theta to both sides. Well, if I did that, I'd get 5, the integral of e to the minus theta cosine 2 theta d theta is equal to minus e to the theta cosine of 2 theta plus 2 e to the theta sine of 2 theta. And I want this integral by itself, so I'm going to divide through by 5. So the integral of e to the minus theta cosine of 2 theta d theta is equal to minus 1/5 e to the minus theta cosine of 2 theta plus 2/5 e to the minus theta sine of 2 theta. And since I'm now done taking an integral, I know what that integral is equal to, I now put my plus c. One more is when we have, let's do a definite integral. So I have the integral from pi fourths to pi halves of x times the cosecant squared dx. Again, you want to pick something to be u and something to be dv. So again, we usually like it to get simpler. If you think about all your integration values, can you find the integral of x? Well, yes, you can find the integral of x. It will make it x squared. Not great, because it makes it more complicated than less. Cosecant squared, can I find the integral of that? Well, yeah, isn't the integral of cosecant squared minus cotangent squared? Minus cotangent. So I can find that. So it makes sense because if I let u be x, then it becomes simpler because du would just be dx. And if I let dv equal the cosecant squared of x dx, then I can take the integral of both sides. The integral of v dv is v. The integral of cosecant squared is minus the cotangent of x. So it's a little bit easier to do it that way. Then again, we want to do u times v minus the integral of v du. So u was x. V turns out to be minus the cotangent of x minus the integral of v, which is minus the cotangent of x, times du, which is dx. Oh, so now you go, oh, and by the way, we are evaluating that from pi halves to pi fourths to pi halves, and pi fourths to pi halves. So don't forget that you have those limits. When I did this, I noticed that pi fourths to pi halves, I'm actually can do that one. So I'm going to go ahead and do that one. I need to also do the integral of cotangent of x dx. And if you don't remember these, and I don't at the moment remember the integral of cotangent, so if you don't remember them, you can in fact use other techniques. So we're going to actually try this one with a little bit slightly different technique. I need a little more space. I'm going to move down here. So I'm going to have minus pi halves cotangent of pi halves minus a negative pi fourths cotangent of pi fourths. Plus, I need to do this integral still. So I'm going to keep this as pi fourths to pi halves. Cotangent is cosine over sine. Sorry, I switched to t's for some reason. I don't know why I did that. All right, cosine of x over sine. Okay. So now, when I go to do this, I can find these pieces, this first part here, the cotangent of pi halves is, well, cotangent is cosine over sine. The cosine of pi halves is 1. The sine of pi halves is, the cosine of pi halves is 0 and the sine is 1. So we're going to get 0 here. Minus or plus, because we have a plus there, plus pi fourths. The cotangent of pi fourths is 1. To do this integral, I'm going to go ahead and use u substitution. So sometimes you have to use u substitution. I'm going to let u be the thing in the bottom, the sine of x. Du, the derivative of sine, because it's in the bottom, that's why I considered it to be the u. My du, therefore, would be the cosine of x dx. And notice I do have a cosine of x dx here. So this would become the integral of 1 over u du. But, yeah. So I have that. Everything's good, except I do need to change my limits. My limits were x is equal to pi fourths. Therefore, u would be the sine of pi fourths. And the sine of pi fourths is square root of 2, 1 over the square root of 2. And then x is equal to pi halves. The sine, u would therefore be the sine of pi halves. And the sine of pi halves is 1. So this actually is from 1 over the square root of 2 to 1 as my new limits. So I have pi fourths plus the integral of 1 over u is the natural log of the absolute value of u. I'm going to evaluate that from 1 and square root of 2 to 1. So we get pi fourths plus the natural log of 1 minus the natural log of 1 over the square root of 2. So that gives me pi fourths minus the natural log of 1 over the square root of 2. And there's my answer. The last thing I just want to mention, this is a problem from the textbook, is what we call the reduction formulas. The reduction formulas actually come from doing integration by parts. So I can actually prove the reduction formulas by doing integration by parts on these. It turns out if I did integration by parts on the integral of cosine of to the nth power of cosine of x dx is equal to 1 over n cosine of x raised to the n minus 1 power times the sine of x plus n minus 1 over n, the integral of cosine of x to the n minus 2 power dx. Then you just use the reduction formula again. So this is the formula again. We can do integration by parts to prove it. I'm actually going to just use it. So here I have the integral of cosine squared of dx, and I'd like to find out what that integral is. So if I want to find out what that integral is, I'm going to go ahead and think about this as being using this reduction formula. I know as I have cosine squared of x dx. That means my n is 2. So in this formula, everywhere I see an n, I'm going to put a 2. So I have 1 over 2 cosine of 2 to the 2 minus 1 of x, sine of x, plus 2 minus 1 over 2, the integral of cosine of 2 minus 2 of x dx. That will get me 1/2 cosine of x times sine of x, plus 2 minus 1 is 1, so I get 1/2 the integral, well, cosine x to the 2 minus 2, this cosine is a 0. That's 1. Because anything to the 0 is 1, except, of course, 0 itself. Then it's indeterminate. So we get 1/2 cosine x sine x plus 1/2 times the integral of 1. The integral of 1, of course, is just x. Since we're done doing integrals, you put in the plus c. So that's how we use the reduction formulas. The reduction formulas are in textbooks, they're online, they're in tables of integral formulas, and that's how to use one of those.